channel Math with Twins. As we all know, we are doing integers. So we are continuing the rest parts right now. But if you want to watch the previous videos, you can always check out the ID cards in the description box below. Let's quickly go to our today's topic, which is nothing but properties of integer. We will be discussing on properties of integers, specifically over addition, subtraction, multiplication, as well as division. So we'll be going on to properties of integers over addition. Let's go to the first property, which is closure property. It says that the addition of two integers is always an integer. So generalized form says m plus n equals integer, which is integer, and integer addition gives us integer itself as the answer. Let's see through examples. Example 1, 2 plus 8, which equals 10. So 10 is an integer and 2 and 8 are also integers. So addition of integers results in an integer. And second example, negative 80 plus 200, which are integers, equals 120, which is also an integer. So here also addition of two integers is also an integer. Thus closure property holds good. Closure property is our next property. The addition of integers is always commutative, is what the commutative property says. Generalized form is m plus n equals n plus n. Let's see through an example where m's value is 8 and n's value is 10. So let's substitute the values for the formula m plus n equals n plus n. So it results 8 plus 10 equals 10 plus 8. And we need to further calculate it, which will give 8 plus 10 equals 18 and 10 plus 8 is also equal to 18. So the commutative property holds good as LHS equals RHS. Associative property says that the addition of integers is associative. Let's see through generalized form. L plus m plus n equals L plus m plus n. Let's see through an example where L equals 5, M equals 8, N equals 9. The example is simplified by substituting these values where we get the same answer, that is answer tallies in both the sides. So associative property of addition holds good. Existence of additive identity of integers. It says that the additive identity of integers is 0. Let's go through generalized form, which is 0 plus n equals n plus 0 equals n. It says there is no problem in changing the position of values. The answer results the same. Let's go through an example where n is equal to 4. And we have simplified it further and our answer is 4 and it tallies at both the sides when we simplify. So our existence of additive identity of integer holds good. Existence of additive inverse of integers. It says additive inverse of integers is the negative of a number. Generalized form is the stick it out. Let n be a number and n dash be the negative of number. That is additive inverse of n, which implies n dashed plus n equals 0. Examples, we have two examples. Let's see them. First one is negative 5 plus 5 equals 0. Negative 90 plus positive 90 is also equal to 0, which says existence of additive inverse of integers holds good. Properties of integers over subtraction is our fresh topic. Let's go through our first property, which is closure property. It says that the subtraction of two integers is always an integer. Let's go through a generalized form. Difference of m and n equals integer. That is, difference of integer and an integer results in integer itself. Let's go through examples. Difference of 10 and 8 gives us 2, which is an integer. Difference of 200 and 80 gives us 120, which is an integer, which says closure property holds good for subtraction. Commutative property. It says us that the subtraction of two integers is not commutative. Let's go to generalized form, which is m minus n, that is difference of m and n is not equal to difference of n and m. That is, the position change will not result in the same answer. Let's go to proof. We have substituted the values for m and n and we have simplified, and we have noticed a difference in both the cases answers. So which says the commutative property of integers over subtraction does not hold good. Associative property. It is that the subtraction of integers is not associative. Let's go through generalized form. L minus m minus n is not equal to L minus m minus n. So let's go through proof, and we have substituted the values of L, m and n respectively as -4, 2 and 3. We have simplified them and we have got -3 and -9, which are not equal. So it says us that associative property of integers of subtraction does not hold good. Now we have existence of identity of integers for subtraction. It says that the identity of subtraction of integers is not at all possible. Existence of inverse of integers for subtraction says us that the inverse for subtraction does not exist. It's time for properties of integers over multiplication. Let's check out the first property, which is closure property as usual. The multiplication of two integers is always an integer is what the closure property communicates. Just go through a generalized form which is displayed here. It says m multiplied by n equals integer, that is, integer multiplied by integer results in an integer. There are two examples. Let's check out the first example quickly. 2 multiplied by 8 equals 16, which is an integer, and second one says -80 multiplied by 200 gives us -16,000, which is also an integer. This shows that the closure property of multiplication is holding good. Property is our next property to be discussed. The multiplication of two integers is always commutative. Yes, it is. Now its generalized form is m into n is equals to n into m, and m and n are two integers. Now let's prove the property with an example. Let m be equal to 8 and n be equal to 10. Now write down the generalized form and multiply in the order. First should be 8 and next should be 10 in the first case, and the second case 10 should be first and 8 should be last. When we multiply, we get both the product 80. Hence, the commutative property of multiplication holds good. Associative property of integers over multiplication. The multiplication of integers is associative. We know that associative property is the change of brackets portion. Thus, its generalized form is L into m into n is equals to L into m into n. Note the brackets portion here. Example, we'll assume that L is equals to 5, m is equals to 8, and n is equal to 9. and so we'll get one case 5 into 72 and the next case 40 into 9, but both the products are same, that is 360, and thus associative property of multiplication holds good. Distributive property is our next property. The multiplication of integers over addition and subtraction is distributive. This is the case. Now let's see the generalized form 1. Solve the example, prove the property and go to the next form and example. L into M plus N is equals to O into M plus L into N is a generalized form for distributive property of integers of multiplication over addition. Now when you substitute the value, the generalized form is assuming numbers, that is L is equals to 1, M is equals to 8, N is equal to 3. We get both the sides 11 and the distributive property is proved. Moving on to the next example and form. The example, let's check it later. First the form. The generalized form says that L into M minus N is equals to L into M minus L into N. We see the difference between generalized form 1 and generalized form 2 is that replacing of addition sign to the negative sign in the generalized form 2. Moving on to example 2, we have substituted the value of L to 1, M to 8 and N to 3 and solved as per the form. We'll get both the sides 5, hence the generalized form is proved here also. So the distributive property of multiplication of integers holds good over addition and subtraction. Moving, existence of multiplicative identity of integers. Identity of integers is 1. Now let's see its generalized form. It says us that n is an integer and 1 into n is equals to n into 1 is equals to n. Okay, now keeping this formula in mind, let's assume that n is equals to 10 and substitute the value, which will result in 1 into 10 equals 10 into 1. And 1 into 10 is equals to 10 and 10 into 1 is also equal to 10, which will give us 10. So the generalized form as given n when multiplied 1 into n is equals to n into 1. So the answer is correct, that is n value and our product value is same. Thus the existence of multiplicative identity of integers holds good. Existence of multiplicative inverse of integers is our next topic. Multiplicative inverse of integers is the reciprocal of that number. The reciprocal of the number means in the fraction the numerator becomes denominator and denominator becomes the numerator. Generalized form is n into n dash, which is equals to 1, where n is the number and n dash is the reciprocal of that number. Moving on to examples. 5 into 1 by 5 is equals to 1. I told you reciprocal means in a fraction numerator becomes denominator and denominator becomes numerator. But what exactly is this? Now let's see. Yeah, there are example 5 into 1 by 5 here. I'll explain with it. Which is understood as a 5 in its fractional form is 5 by 1. And the 1 becomes the numerator and 5 becomes the denominator when it comes to reciprocal, which will give us 1 by 5. And then multiply 5 into 1 by 5. 5 and 5 gets cancelled off, which will result in 1. Thus, the identity is formed when we multiply. Next, 90 into 1 by 90. Here, 90's reciprocal is 1 by 90 because it understood in the fractional form of 90, 90 by 1. Numerator 1, denominator 90 as a reciprocal. So 90, 90 gets cancelled off, which will result 1. This is how the existence of multiplicative inverse of integers holds good. Our next topic is properties of integers over division. By now we know what is the closure property. Hence, the division of two integers is not always an integer. This is because when moving to an Example 20 by 5, we'll get 4, which is an integer, but 90 by 100 is equal to 0.09, which is not an integer. Hence, it means the division of two integers is not always an integer. Sometimes it may be and it may not be. So our generalized form is equal to m divided by n is not equal to integer, and m and n are integers. That is why I have written in the below step, integer divided by integer is not equal to an integer. Moving on to the property of integers over division. The division of two integers is not commutative, and the generalized form is m divided by n is not equal to n divided by m, and there is a proof. We have assumed m is equal to 10 and n is equal to 5 in first case. M divided by n, we got quotient 2. In the second case, n divided by m, we got the quotient 0.5, and we know that 2 and 0.5 are not equal, hence the commutative property of integers over division does not hold good. Property, the division of integers is not associative. Generalized form is that L divided by m divided by n is not equal to L divided by m divided by n. The proof is that 3 is not equal to 0.1875. The associative property of division does not hold good. Next is the distributive property. Distributive property. The division of integers over addition and subtraction is not distributive. This is generalized form 1. It refers to distributivity over addition. L divided by m plus n is not equal to L divided by m plus L divided by n. We have given specific values for m, L, and n. That is, L is equal to 8, m is equal to 3, n is equal to 1. And when we have substituted them, these values to generalized form, we got as the 1 and 4 by 3, and another case 6. We know that 4 by 3 and 6 are not equal, hence this property does not hold good. Next property is the distributive property over subtraction for division. L divided by m minus n is not equal to L divided by m minus L divided by n is the generalized form, and with the same values, that is L is equal to 8, m is equal to 3, n is equal to 1, and the generalized form 2, we have substituted the values and we got 4 at one end and negative 2 at another end. We know that 4 and negative 2 are not equal, hence this property also does not hold good. Hence the division distributive property, either subtraction or addition, does not hold good. Existence of identity of integers for division. The identity for division of integers does not exist. Existence of inverse of integers for division. Inverse for division does not exist. Summary of the entire video is displayed for you. You can check out. For more time, pause the video. Thank you for watching the video. Please share, like, subscribe our channel, and press bell icon nearby for notification of more videos. For doubts, as usual, leave a comment below.